Hello everyone, this is Mr. Havenhill, and I wanted to go over a couple of the homework assignment questions from last night that I know some folks were struggling with while in class. I wanted to look at specifically number 7 and number 9, and I hope that this will be helpful to you. So here we go. Number 7. We're going to try to determine whether this bad boy right here is convergent or divergent. And if it's convergent, we want to determine if it's convergent absolutely or conditionally. So the first thing we want to do is determine a sub n, and since this is an alternating series, a sub n is just going to be 1 over n times the natural log of n. Well, my first question is this: being that we're dealing with an alternating series, can we apply the alternating series test? Well, let's determine two things here. Number one, let's compare the nth term to the nth plus first term. So how does 1 over n times the natural log of n compare to 1 over n plus 1 times the natural log of n plus 1? Well, if we aren't completely sure, we could definitely try plugging in some numbers. I think most of us can see that this right here, we're dividing 1 by a smaller number than this would be, and so therefore this should be larger. But if you are unable to see that, that's totally fine. Try a number. In this case, we're going to let n equal 2, and you'll notice that that's what our series started with. Some of you might have said, well, why not 1? Why didn't it start at 1 this time? Well, if we would have plugged in 1 here on the bottom, we would have had the natural log of 0 on the bottom, or natural log of 1, which is 0 on the bottom, and that would have been a big mess. So if we plugged in n equals 2, then we would literally have 1 over 2 times the natural log of 2, trying to compare that to 1 over 3 times the natural log of 3. And the decimal value of this is approximately 0.7213, and the decimal value of this is approximately 0.3034. And well, the nth term is clearly greater than the n plus first term. So the first condition is met. And how does the limit as n approaches infinity of our series, how does that behave? Well, in this particular case, we are definitely going to get a limit that approaches 0. And so by the alternating series test, we have that this series is going to converge. Well, now let's see how it behaves when we're absolutely or conditionally. And so by the alternating series test, a sub n is going to converge. But is it going to be conditional or absolute? So our next step then is to consider this. Consider the series where we take the absolute value of every single term. In that case, we're just simply looking at this right here. And so what we're looking at then is a question: how do we determine whether this thing converges or not? And our first reaction might be to say, ooh, let's compare this to a p-series, specifically the harmonic series 1 over n. How does 1 over n compare to 1 over n times the natural log of n? That would be our first inclination. If you thought that, awesome, well done. The only problem is if you try plugging in numbers, what we end up finding out is that 1 over n is greater than 1 over n times natural log of n. And so unfortunately, this comparison says nothing. It doesn't give us any ability to determine the behavior of the smaller series. So, what do we do next? Well, at this point, we start looking through our list of tools that we've developed, and if the direct comparison test doesn't work, and we're trying to determine the convergence of this particular series, I wonder if the integral test would work. Well, do we have a series that's decreasing? Yes. Are they all positive? Yes. Awesome. So this is a perfect candidate for the integral test. And let's go ahead and let's see what happens. So let's see what happens, folks. What we want to do is look at this particular series, and what we're going to try to do is model it. We want to model it by the integral from 2 to infinity of 1 over x then times the natural log of x dx. And we simply want to ask ourselves now, how would we integrate that? Well, this is what we've been working on all semester long. I mean, we started with improper integrals in January. And so let's go ahead and let's do a u substitution. Let u equal the natural log of x, then du would equal 1 over x dx. And I'm looking at this integral, and we have the integral of, what is that going to be? 1 over u du. And if I were to do a direct substitution here, u of 2 would be the natural log of 2, and then u of infinity would just be infinity still. And let's integrate that, and we're going to take the, well, actually I'll do it the formalized way, as take the limit as a approaches infinity of the natural log of 2 to a of 1 over u du. Then we can go ahead and integrate that, and we get the natural log of u evaluated from 2 to a, which is going to give us, that'll give us the natural log of a minus the natural log of 2. And this right here, well, we would be tempted to say, well, it definitely is going to diverge, but we have this piece right here that we're subtracting. So let's just combine these first. Let's do all the algebra we can with natural logs before we evaluate the limit. So in this case, some of you might be saying, Mr. Haven, I don't think that's going to make much of a difference. And you're right. In this particular case, after we've done all the possible algebra we can with the natural logs, when we evaluate this limit, we still get something that's going to diverge. So ultimately, what did we just do? We just showed that this series diverges. We took the absolute value of our series by the integral test. And since the absolute value of the series diverged, but we were able to show that the series converged by the alternating series test right here, that means that this series converges conditionally. Do number 9 real quick from the assignment, and this one goes by much quicker. At first glance, we're looking at this and it's a little intimidating. We've got the cosine of n pi, natural log of n, quantity squared, and it might not be immediately recognizable what this is, so let's plug in some values and let's see what happens. So this is a series that starts at 2. Similar to the last one, if we would have started at 1, that would have given us a 0 in the denominator, and we know that's a no bueno. So let's go ahead and let's see what this looks like in terms of our first few terms. We would have, for our first term, n equals 2, the cosine of 2 pi, and that's just 1. And then that would be the natural log of 2 squared. All right, let's see what happens next. Let's plug in 3. The cosine of 3 pi, ooh, that's negative 1. And then that's going to be the natural log of 3 squared. And we plug in 4, and we have the cosine of 4 pi, and well, that's just 1 again. And let's go ahead and let's see what happens one more. Plug in 5, the cosine of 5 pi, well, that's negative 1, and I smell a pattern. And so now that I can see what's happening here, that I've expanded this, this is clearly an alternating series. And essentially, because of the way this numerator is written, the cosine of n pi is alternating between 1 and negative 1 throughout this entire length of the series. And so what we can do is try utilizing the alternating series test at first. So let's see what happens. We're going to let a sub n, oops, I ran out of room here. Sorry about that. Let's fix that. Let's let a sub n equal 1 over the natural log of n, 1 over the natural log of n squared. And what we want to do first is compare how does the nth term compare to the nth plus first term. And well, the natural log of n function is an increasing function, and as a result we know that this value here is going to, natural log of n plus 1 is going to be bigger than the natural log of n, and when you square those values this is going to even be bigger still, and when you divide 1 by a bigger value it will be smaller than 1 divided by a smaller number. And so the first condition of the alternating series test holds. And then let's go ahead and let's check out what happens when we take the limit as n approaches infinity of a sub n. And, well, we end up with 1 over essentially infinity, and so, which is 0. And so by the alternating series test, we know that the series is going to at least converge. So now the question is, will it converge absolutely or conditionally? Well, let's go ahead and we should always try with the comparison test. Let's see what happens there. And so we're going to investigate this right here. What is this particular series? How does it behave? So let's see what we've got here. That's going to be 1 over the natural log of n squared, and we're going to take the series as we go from 2 to infinity, and so that's 1 over the natural log of 2 squared plus 1 over the natural log of 3 squared plus so on and so forth. And the first question I want to ask is, can we compare this to something, and how would this series compare to the harmonic series? We know that this thing is going to be divergent, and so I'm just pulling something, just making an attempt here. It may or may not work. It may take me down a dead end. So let's see what happens. Off the top of my head, I can't tell what this is going to be. So let's investigate what happens. Let's try n equals 3. So that's going to give me 1 over 3, and we want to know how does that compare to 1 over the natural log of 3 quantity squared. Well, I'm going to need my calculator on this one, and I've got that this is 1/3, and I've got over here that this is 1 over 0.8285. And what we have is that this guy right here is clearly larger. Well, why is that important? Why is that important? Let me make this a little easier for you to see. We have that a smaller series diverges, and so the bigger series must then diverge too. And that's how this is going to work. And so by the direct comparison test, or a basic comparison test, there again, those are synonyms, the absolute value diverges. Therefore, this particular series converges conditionally.